Problem number 1, we are given with a soil profile shown in the figure. We are asked to calculate the variation of the total stress, the pore water pressure, and the um, effective stress with depth. Second is if the water table is rises to the top of the ground surface, what is the change in the effective stress at the bottom of the clay layer? And the third is how many meters must be the groundwater table rise to increase the effective stress by 15 kilonewtons per cubic meter at the bottom of the clay layer. First is we need to calculate the variation of the total stress, the pore water pressure, and the effective stress with its depth. The formula that we will be using is effective stress is equal to the total stress minus the pore water pressure, or the total stress is also equal to the unit weight and its depth or height. The solution for this is we need to substitute the given from the dry unit weight of sand, which is equal to 2.66 plus that would be 0 over 1 plus 0.52 multiplied to the unit weight of water, which is equal to 17.17 kilonewtons per cubic meter. So now we have the dry unit weight. We can now solve for the total stress, which is equal to the unit weight of the dry sand times its depth. So that would be 17.17 times 5, which is equal to 85.84 kilonewtons per cubic meter. Because it is not submerged in water, therefore our pore water pressure is equal to 0. That would give us the effective stress equals to the total stress. Now on the unit weight of the saturated layer, which is the clay, that would be equal to 2.75 plus the degree of saturation 1 times 1 over 1 plus 1 times the unit weight of water, which is equal to 18.39 kilonewtons per cubic meter. Now we will solve for the total stress, which is equal to the dry unit weight of sand times its height plus the unit weight of the saturated clay times its depth. That would give us that would be 85.84, which was calculated from the previous plus 18.39 times 4, which is equal to 159.41. So this is now our total stress. Now we will solve for the pore water pressure, which is present in this depth. The unit weight of water times its height, which is 9.81 times 4, which is equal to 39.24 kilonewtons per cubic meter. Since we had calculated the unit weight and the pore water pressure, we can now solve for the effective stress, which is the difference of the total stress and the pore water pressure, which is 159.41 minus 39.24, which is 120.17 kilonewtons per square meter. Second question is, if the water table rises to the top of the ground surface, what is the change in effective stress at the bottom of the clay layer? So meaning the sand is now saturated. So we will solve for the saturated unit weight of the sand layer. That would be equal to 2.66 plus 1 times 0.52 over 1 plus 0.52 times the unit weight of water, which is equal to 20.52 kilonewtons per cubic meter. And we can directly solve for the effective stress. Unit weight of the saturated sand times its height plus the unit weight of the saturated clay times its depth minus the pore water pressure, the unit weight of the water plus the height of the sand and clay. That would give us 20.52 times 5 plus 18.39 times 4 minus 9.81 times 4 plus 5, which is equal to 87.87 kilonewtons per square meter. So the change in effective stress will be the calculated effective stress, which is 120.17 minus the effective stress for the water table rises at the top surface of the ground. So that is 87.87. Now we have the change in effective stress, which is equal to 32.30 kilonewtons per square meter. The last problem is how many meters must the groundwater table rise to decrease the effective stress by 15 kilonewtons per cubic meter at the bottom of the clay. So we have a given effective stress decrease, which is 15 kilonewtons per cubic meter. We can equate this using the formula. Effective stress is equal to total stress minus the pore water pressure, which is the effective the total stress is equal to the height of the sand layer minus the unknown height times the unit weight of dry unit weight of sand plus the saturated unit weight of sand multiplied by the height, which is unknown, plus the unit weight of the saturated clay times the second height, which is 5. Now we have this equation. First equation, 5 minus h times 17.17 plus 20.52h plus 73.56. Now our pore water pressure is equal to 4 plus the unknown height multiplied by the unit weight of the water. Substituting the decrease in effective stress to our effective stress, 120.17 minus 15 is equal to the total stress minus the pore water pressure. By using our calculator, we can have the value of 2.32 meters.